Meteorology 330 Exam 2 Study Guide Fall 2021. Section 1. Forces and Balanced Flow. The differences between an inertial and a non-inertial reference frame. In an inertial reference frame, it is a frame where the object does not change its speed or velocity. For example, two objects inside of a car. The reference frame is uniform/constant. In a non-inertial reference frame, it is a frame that is accelerating relative to the inertial frame of reference. For example, viewing object A inside of a moving car from point B outside of the car. The frame is non-uniform/moving. Be able to recognize the following forces and equations: pressure gradient force, Coriolis force, gravity, viscous/friction force, and centrifugal force. Be able to recognize them all in height, isobaric, and natural coordinates. Pressure gradient force is often seen as d phi dn in natural coordinates. Coriolis force is often seen as the Coriolis parameter multiplied by the wind vector. And the Coriolis parameter is equal to 2 omega times the sine of the latitude you're at. Gravity is recognized as g, which is equal to 9.81 meters per second squared. Viscous/friction force is the constant k multiplied by the Laplacian of the wind squared times the wind vector. And centrifugal force can be described as the wind vector squared divided by r, and r is the radius. In geostropic balance, the Rossby number will be less than or equal to 0.1. In cyclostropic balance, the Rossby number will be greater than or equal to 10. In inertial balance, the Rossby number equals 1. And in gradient balance, the Rossby number is between 0.1 and 10. Remember that the Rossby number can be described as centrifugal force divided by the Coriolis force. So, it makes sense that in geostropic balance, the Rossby number would be extremely small, because geostropic balance involves no curvature of the wind, and curvature is required for centrifugal force. And cyclostrophic balance is a balance between the centrifugal force and the pressure gradient force, with Coriolis force being negligible. So it makes sense that the Rossby number would be large, greater than 10. Natural coordinates. In natural coordinates, we need not worry about the wind direction because wind speed is in the t direction, and the n component of the wind is 90 degrees to the left. The natural coordinate system essentially moves with the direction of the wind. The Ekman layer is the layer extending from the surface to where geostropic wind begins. In the Ekman layer, friction force acts opposite of the velocity vector, and pressure gradient force still always points toward areas of lower pressure. Remember that the Coriolis force has its magnitude proportional to the velocity of the wind, so when you slow down the wind, the Coriolis force becomes weaker and the wind curves in closer to the pressure gradient force in terms of direction. In geostropic flow, the Coriolis force and the pressure gradient force are equal and opposite forces, with the pressure gradient force pointing toward areas of lower pressure. PGF equals negative CF. Gradient flow represents a balance between all three forces. The centripetal force always points outwards, and the Coriolis force always points opposite of the pressure gradient force. And there are 4 types of force balance diagrams for this kind of flow. In a regular low, the flow is counterclockwise, as you would expect from a low, and the PGF points inward toward the center low, of course, and the Coriolis force points outward. In an anomalous low, flow is clockwise, PGF points inward once again, and the Coriolis force points opposite of the PGF outward. What differentiates the flow direction between the two lows is that one of them is in the northern hemisphere and one of them is in the southern hemisphere, with the regular low being in the northern. And thus, for a regular high, PGF points outward, Coriolis force points inward, centrifugal force points outward, and the flow is clockwise. And for an anomalous high, all those forces are the same, except the flow is counterclockwise, because the high is in the southern hemisphere. For highs only, PGF has a limit to how strong it can be compared to the other forces. And this limit of strength is defined by the Coriolis factor squared times the absolute value of the radius divided by 4. And that has to be greater than or equal to the pressure gradient force. In cyclostropic flow, it is a balance between the centrifugal force and the pressure gradient force. So Sen equals negative PGF. And cyclostropic flow is always a low, and it's an organized flow. It occurs where Coriolis force is very negligible compared to the other two forces. This would be at the equator or a very small but strong rotation like a water spout. If the wind is calm, there is also no Coriolis force. Inertial flow represents a balance between the centrifugal force and the Coriolis force, meaning centrifugal equals negative Coriolis force. This is flow under conditions with no pressure gradient force, meaning no pressure gradient. The rotation of this depends on the hemisphere. In the northern hemisphere, the Coriolis force is to the right, which means counterclockwise rotation. The Coriolis force is inward and the centrifugal force is outward. In the southern hemisphere, Coriolis force is to the left, which means clockwise rotation. And the Coriolis force is inward once again, and the centrifugal force is still outward. The key conditions in which a force goes away. Coriolis force is equal to 0 at the equator or when there is 0 wind speed. The pressure gradient force is equal to 0 in areas of constant pressure, meaning no pressure gradient. The centrifugal force is equal to 0 when you have no curvature in flow at all. Calculating the forces. Coriolis force, or CF, is equal to the Coriolis factor times the wind vector. The pressure gradient force is equal to centrifugal force plus Coriolis force, also represented as d phi dn, where phi is the geopotential height and n is the movement of the natural coordinate system. N can also be x if you're not dealing with natural coordinates. Essentially, PGF is represented by a change in geopotential heights or pressure with distance. When the wind is geostropic, PGF and Coriolis force are equal because there is no curvature, meaning centrifugal force equals 0. The centrifugal force can be represented by the wind vector squared divided by the radius, where r is the radius from the center of rotation. All of these equations will be given on the exam. Just make sure you have them memorized as to which corresponds to which. The depth of the Ekman layer can be calculated with pi times 2k divided by f, all raised to the half power, where k is the viscosity coefficient, and in the Ekman layer, k is a constant of 5 meters squared per second. Calculating u and v at a given height within the Ekman layer. Remember, these following equations only work within the Ekman layer, and they will be provided. Just make sure you have them memorized as to which corresponds to which. So, for the u component of the wind, uz equals ug, or the u component of the geostropic wind, all times 1 minus e to the negative lambda z times cosine lambda z. And lambda can be defined as the Coriolis factor divided by 2k, all raised to the 1/2 power. And Vz is represented by Ug all times e to the negative lambda z times sine lambda z. And remember, z is the height in this case. Make sure your calculator is in radians mode for the equations. Section 3, mass continuity. Remember that the level of non-divergence is the level at which neither divergence or convergence is occurring. And remember the mass continuity principle. Air cannot blast into the ground or go through the tropopause. This means that divergence is always 0 at the ground and at the tropopause. And this means that convergence at the surface must create rising air, and divergence at the surface must create sinking. So, with rising air, omega is negative, and with sinking air, it is positive. This is because omega, remember, is the change in pressure with the change in time. So, as you sink, the pressure around you increases, meaning that omega will be positive. Calculating the surface pressure tendency given the mean divergence over a layer. So this is represented by dp at the surface dt. And that gives you the surface pressure tendency, which is an equation that will be given on the test. And calculating the vertical air velocity given the mean divergence over a layer. So this is represented as omega pt, as in pressure at the tropopause. Once again, this will be given on the exam. Section 4, final section, the thermal wind equations. And thermal wind, V subscript T, can be defined as Vt equals Vg upper minus Vg lower. And it is simply the geostropic wind in a higher or upper layer minus the geostropic wind in a lower layer. Remember that Vt itself is not a wind vector. It is the difference between two wind vectors. And the equations for this will also be given on the test. But just remember when you're looking for the equations that ut is the u component of the wind, and v, lowercase vt, with no vector, is the v component of the wind. For veering and backing, remember that veering is clockwise rotation of the wind and is associated with warm air advection. Backing is counterclockwise and is associated with cold air advection. And this is veering and backing with height. So as you go up, the rotation backs. It goes counterclockwise. And the opposite with veering, where it becomes more clockwise as you go up.